Our next speaker is Andrey Tsyganov from the University of Groningen, and his talk is entitled iRODS Labels, a proposal for a complementary labeling mechanism in iRODS.
Yes, hi everyone, good morning. Yes, I'm the member of the RDMS team in Groningen, and we are developing this system on top of the iRODS, Research Data Management System. And today I will present the proposal of improvement that can be done within the iRODS core that might really help to solve existing metadata complexity issues in the iRODS. So I'll start with introduction, then the iRODS labels architecture and implementation, then the iLabel tool, the Python client for the RPC or PRC, iRODS labels results and future suggestions, and small example with the screenshots that I've made during the development. So, introduction. As we all know, we have a tree with the collections and data objects within the iRODS, and the current well-known and quite useful great mechanism of the AVUs has the following structure. So each AVU key value pair, key value unit pair actually connected directly to collection or to the data object or to the resource, but resources are a bit out of scope here. And the thing is that if you want to tag all your objects with the certain parameter or with a certain value to be searchable by the metadata, you need to tag them all. And if you change this value, you need to update all. And that's quite hard to follow and trigger and make the metadata consistency across multiple objects. So the structures of AVUs are flat by design, so no hierarchy. And if you want to do a schema validation on the metadata, you need to do it out scope. So like the value might be too small for the big schema. We came to this idea a long time ago when we started to develop the RDMS at RUH, and when we started to apply the metadata templates. And it happened that if we want to do the metadata template for the large amount of data, we need to choose a strategy, well, how to do that. For instance, we've made a choice that we tag the top collection and then artificially make a decision that all underneath data are actually tagged with this same metadata template. And then if there is another metadata template inside this collection, then the top metadata template so the lowest metadata template is the main for the objects beneath. And the idea came out naturally that what you can do is effectively create the metadata, which is the entity, and I call it labels, that you mark your objects and collections within the one value and name. So the proposal is to introduce the label that has its tag, like you do it with the email, and then the value also separately. So, and this leads to the architecture and implementation of the prototype. And here I must say, so labels are the new metadata type that lives alongside AVUs. They works together. Each potentially has its own great advantages. And label has a name, description, and the value for validation. Because then if we take the value as a large JSON, we can put aside also the validation schema straightforward. Also, labels can be architectured as a tree. So you have a parent, main one, then sub-label, etc. And that works well for the iRODS. Within the iRODS, if you need to implement the publication templates, for instance, for different scientific areas. And also, labels should have separate ACLs. Then it will be easier to distinguish the visibility for the labels and the actual data. And I must say, regarding to the previous talk from Terrell, that, well, this project used actually Claude AI as a project assistant, as the passes that I've chose for prototyping was actually compile iRODS from the scratch and inject some code into the core of iRODS. And I must say that actually the core code was not really changed dramatically. I'll show it. So we're starting from the database schema that we propose. And there are a number of tables. So label is the basically name and visibility. So you can make a public or private label. So any user can search for the label name or just certain with ACL restrictions. Value is a separate table that stores JSON and validation JSON. Label access is the label ACL. And then data label and collection label, those two are actually connecting label ID with the data ID or label ID with the collection ID. The challenging part here is how you propagate the data workflow and consistency. Because if you have a object under this certain label and this in a collection, and then it's inherited, so that all other collections or data objects should have the same visibility and the same label. So how to propagate this? It's approximately the same task how you solve it for the AVUs as well. And there are two strategies. One, actually, as my background are databases, is to use a foreign keys, which is now not in the iRODS schema, and that would be the easy solution. And the another part is to change the DB plugin CPP, which is more challenging, but also the amount of code needed is not huge. So the schema itself, as you can see, allows to do the R label table self referenced. So that builds the tree. On the left, you see the V label tree view that implements a recursive query, the standard one for all relational databases in the SQL syntax, so that it helps to see the tree directly. And the structure, basically all tables are connected within the label ID, and the iRODS default database schema only participates in the R data label and collection label by the IDs of the collection and the data object. These slides are informational, so I've built the Vagrant VM to test the implementation and run the code, compile the iRODS from the scratch, from the source, and use the version 4.3.5 for tests, because at RUH at the moment we're using the 4.3 version. And just the tools that happen to be needed for source compilation. So I've providing it for the information that if anyone reads the presentation afterwards, so sees that what was actually used. I must say that the compilation stage was quite challenging, but that worked quite well. So the core of the implementation is was to add the API, so the new number API 2000 to iRODS, and then create the RPC or PRC calls that other clients would use. So like the tool iLabel would actually call the server to use the APIs on the server side. So thus any other clients would also benefit from those. And of course, to do a gen query and gen query 2 changes so that those can be also benefiting from the new mechanism. On the left side, you see actually the files that were changed during the project. And I must state that DB plugin CPP is, in that sense, optional. It's very large file. And others injections were quite straightforward. So this is on the left, it's a project new files. So the iLabel tool, the server CPP file, and some Python client implementations. And there's basically the list of the files that were changed. And I'll skip it a bit because more important that what was changed. So this is for the gen query part. Effectively, this code was added to the files, and that's basically it. So on the compilation stage, we compile the new tables, then we add those lines into the dedicated files, compile the iLabel, and that's it. So effectively, this all what's needed. The amount of code that needs to be added to the source is very, very little. So then, how it works? There's a key architecture question on how to implement consistency. Because if you have inheritance true, then you need to recursively call the objects. And there are two options, effectively, as I told, or to use modifications in the DB plugin or on delete cascade, for instance, in case of deletion. And that's an architecture decision. In this case, for the demo, I use the DB plugin change. So the iLabel tool. iLabel is an extra iComment tool similar to standard iRODS commands, and it used absolutely the same even code pattern. So 0 SQL all goes to RPC, well, PRC, and goes via API, registered API 2000 that operates with labels. This is the flow. And here you can see on the comments part what actually is available in iLabel tool. So you can add label, delete label, get set value for the label, set visibility, search for the label itself, search children, pass tree, add, attach or detach data object, add collection, or recursively add collection. So everything from the collection is added to the, so marked with the label. List data, list collection, list label, search by value, which is quite handy. And list data by value and list collections by value attached with this certain label value. So if you, I will show an example later what that actually means. Then grant revoke, effectively, if you want to grant user the permission to see the label or to see the value. And then it all goes through the RPC or PRC. That's, I'm always a little bit doubtful how to call it properly. Examples of the commands of the iLabel. So that's what you can use. And the same will go for the Python. So we are using the Python iRODS Python client at RDMS project. And that's why I was also interested to implement the labels prototype within the Python code. And the idea is the same. So I've tried two paths. One is just to call the iLabel as a sub-process in Python. That worked quite well. And also as the native call, so to RPC within the same route of using the server-side calls in that sense. And then how it will look for the native. So basically, you import the class, you instantiate the session, and then you have the same add label. So we add a label to operate with, attach to data. So those data will be marked with that label, and grant the label to the user Alice in this case. It's just a common name for the example. And then list data by label, so you will effectively will see your newly attached object. So the current result is a plugin that compiles successfully within an iRODS core. Labels provide additional functionality for tagging and data management within the iRODS. iRODS labels is not a replacement, but rather an addition to existing AVUs. And both has their own great value, I think, for the data management within the iRODS. And future here is, of course, lots of questions. In principle, what's not implemented with the proposal, MySQL and Oracle databases. However, the SQLs are pretty standard, so I don't see, I do not foresee any issues there. Integration to the iRODS would help avoiding the compilation, of course, but that's my proposal to a consortium, or our proposal to the consortium in that sense. Maybe this development will look interesting. And DB plugin verification, that's where lots of question might be, because it's core workflow of the iRODS, so the transactions should be kept properly isolated, and the consistency should be guaranteed. What else is possible? The cross-tree references for labels. So if label now can have only one parent, but practically nothing stops from having multiple parents, and then it would allow reusage of the labels across the horizontal scaling in a horizontal way, not only vertical. And versioning, so for values, and this handy for metadata templates. So with the evolution of the certain values, you might have a different template version, or effectively a different template version for some data, and that the label will stay the same, but the value for the label will change. And I think it's a really minor, strategically, it's a minor update for the metadata, which will impact a lot. And I have a small screenshots as an examples. So here you see I'm inside my demo Vagrant machine, and I've created some folders and some data objects. And I've created the label for publication metadata. So publication iRODS label UGM2026. Then on step 3 of the test, I've added the values and the validation schema aside of that value. Then I list so I've attached recursively all objects in the top folder within the label. And now I can list the data and the collections that belongs to that label directly. And you see the search pattern is quite nice, because you get the label name and then only reference the IDs. So this is really fast, even with the left and right truncated search. Especially if we looking into the validation by value. So this is the iLabel command get the label itself. So it returns the value and when it was modified. And then I can list the data by value. So I search in the value with the left-right truncated search. We do not expect lots of values to be in the database in this case. Well, let's say 1,000. Well, even if there are 10,000, it's still fast. And then search by ID is also fast. So you don't have,
Can you hear me?
Yep.
Just one more minute, and then we can go into questions.
Yep. 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 That's great timing, actually. So then it's fast, and you solve the current AVU problem if you look for the value or the key by the left truncated, right truncated. You almost inevitably hit the full scan in this case, except of the filter by the object path itself. So then you see I've modified the value on the top comment, and then we've got the search by the new value, and I still see the same list of values of objects. And the last bit of a test, that I've added a new folder and the data into the demo folder, and search by value again, and they are marked again and found. So these are the operations that available then within the plugin. And thank you very much for your attention.
Thank you. Do we have any questions? We have one right here.
Hi, thanks for the presentation. Do you have like any benchmarks of like if you are comparing AVU metadata versus these labels in a large collection?
No, I cannot cannot say the benchmarks as this prototyping, so we didn't fit the real data yet. But what I can say that the table size, if you let's say if you label all your objects with the label and with the metadata, the size would be comparable to the metadata table reference. So ID by ID, it will be the same, but the search by value will be faster, because effectively you will scan small table and then get all IDs at once.
All right, thanks.
All right, we are going to move on to the next speaker. Thank you.